Hello students, in this video we'll consider the Hausdorff Moment Problem. The Hausdorff Moment Problem states the following. It says, suppose that f and g are continuous if f and g map AB into R are continuous, such that, and for k equals 0, 1, 2, 3, etc., we have that the integral from a to b of f of x, x to the power k dx is equal to the integral from a to b g of x, x to the power k dx. In other words, these functions f and g have the same moments for every k, same moments. If this is true for continuous functions for every k, then f has to be identically equal to g. Then f is identically equal to g. Okay, excellent. Now, it's important that this region over here is compact, right? If it's an infinite region, I can construct an example of a continuous function that has 0 moments for every, a non-zero function that has 0 moments for every value. Okay, so here's the idea of the proof, right? So what we're going to do is, here's the proof. So proof, define h of x to be f of x minus g of x. Then our condition turns into what? Our condition turns into the integral from a to b of h of x by subtracting over here h of x, x to the power k dx is equal to 0 for all k. Forever? Okay, great. And so now here's the portion where we're going to say, if this is true for every k by the linearity of the integral, we can say the following. So by the linearity of the integral, we have for any n in n and coefficients a0 through an in R, we have the integral from a to b of h of x times the sum, j goes from 0 to n of aj x to the power j dx is equal to 0, okay? Just by the linearity of the integral. And what this tells me is this tells me that the integral of h against any polynomial is 0. So in other words, this implies for every polynomial, p a polynomial, integral from a to b of h of x, p of x, dx is equal to 0, okay? Now I can use since this interval is compact, I can use the Weierstrass approximation theorem. So by the Weierstrass approximation theorem, there's a sequence of polynomials Pn such that Pn converges uniformly to this function, any continuous function in AB, such that Pn converges uniformly to H on AB. Okay? So now what can I conclude? I can conclude now by the uniform convergence, therefore, thus, what can we have? Thus, we have the integral from a to b of h of x dx, h of x squared, for example, h of x squared is going to be the integral from a to b of the limit as n goes to infinity of these polynomials Pn of x, h of x dx. That just comes, that's the definition. Of course, I can pull this limit out of the integral by uniform convergence. So since the convergence is uniform over a compact set, I can pull that limit out. This is going to be the limit as n tends to infinity of the integral from a to b of Pn of x, h of x dx. But I know that hn against any polynomial over here is going to integrate to 0, so this limit is just equal to 0. So that tells me that the integral of h of x squared dx is equal to what? This integral over here is equal to 0, okay? Now, if that integral is 0, that's the only way a non-negative function can integrate to 0. The only way a non-negative continuous function can integrate to 0 over a compact set is the function 0 itself. So this condition over here, so this over here forces, this implies that h of x is identically equal to 0. But if H is identically equal to 0, this implies that F is identically equal to G, and that gives us our proof. So if two probability distributions, so if two probability density functions have this, give rise to the same moment for every value k, 0 all the way up to k from 0, 1, 2, 3, etc., then those probability density functions correspond to random variables that have the same underlying distribution. So in other words, this is a statement about the fact that these probability density functions are equal. In other words, it gives rise to an equivalent class of distributions for random variables. Thank you very much.